Okay, next up is Mario Lovic from the Institute for Anthropology here in Zagreb, and he will give us a brief introduction and overview of machine learning and how it's used in the computational toxicology.
Thank you. Hello, everyone. So the scientific problem, at least the one I had with my PhD thesis, is we need a good risk assessment strategy for chemicals. So you see, this is kind of the graph showing how many hazardous and non-hazardous chemicals are produced in Europe, and it's quite a lot. And the thing with, especially with Europe now, is you have the 3 R's. You should do not so much animal testing, and then you have a problem. How do you find out whether a chemical compound is toxic or not, and how much of a risk does it kind of have on the environment? So, and then we have REACH. I guess most of you know about it. So it's the registration, evaluation, and authorization of chemicals. And, if a chemical is being produced more than 1,000 tons, and it's many of those, you have to have long-term toxicity data on different types of organisms, reproductive toxicity on birds, 2-generation reproductive toxicity, etc. So it's quite a lot, and you can't do animal testing. So kind of, we have a problem with it. And we know, from, for example, from PubChem, there are quite many chemicals registered. So we have kind of over 100 million chemicals which are known or in the databases, and we have good toxicity data on those, maybe for around 10,000 of those. So we're kind of missing, 99 million something. So we're kind of moving in a circle around with not having data which we need for the legislative. And then, this is kind of the eco-toxicological data is kind of what we know least. So we know about the identity of the chemicals. We know about the physical chemical properties. We know some of the bioactivities because most of those are kind of used for drugs. So we know some bioactivities. And then fate and exposure and kind of the toxicological risk, we have a little data on those. So how do we get missing data? So ideally, we would measure them. And then there are some kind of high throughput studies which are done, especially in the US. But we can't do them all. So the more realistic scenario is to build models based on those where we have information on. And how do we build models? So let's kind of have this small interactive round. Okay. The good thing is kind of the central point is data and information, but I like the others as well because kind of they're all converging to what we want to understand. So tox data, which is also data understanding the data, that's very true. Statistic procedure, yes, kind of. Training data, yes, we want to kind of train the model. Computer, Python, it's all there. Code, so we use Python and kind of code to generate these models. Chemical structures is a good point. We'll talk about that as well. Programming skills, yes, but nowadays you have ChatGPT, so you kind of can avoid it quite nicely. Yeah, independent variables, that's all very true. Okay. So I kind of see that you have an understanding on this. So models for toxicity. So we said we do have a few kind of measurements. I mean, a few. We have 10,000-ish maybe comparing to 100 million chemical compounds. So based on those we can build a model. And then we kind of go into the extrapolation phase to kind of get the values where we don't have the data for. Okay, so we have 2 phases. So the first is, I used it here with the use case. So we have, for example, a data set. We process the data and standardize, and then we build a machine learning model, for example, with random forests. We can tune the model, etc. Once we have the model, we can save it, and we can feed it the same type of data to generate predictions for other chemical compounds. So if the model generalizes well, meaning it has a high accuracy, for example, we can apply the model and generate prediction for external data. So I have 10,000 chemical compounds done in a kind of toxicological studies, but I have 10,000 more where I don't have data. So I can generate the model on the first 10,000 and predict on the next 10,000. It's not optimal, but it's the best we have. So if you have 3R limitation and but you need the data, this is the best shot. So the use case I have here is so the goal was to assess risk for chemicals in rivers. It was the Sava River, which is kind of south of it's actually going through city of Zagreb. So we wanted to predict activity and properties based on sparse training data. We don't have so much data available. And we use machine learning, or here we kind of say quantitative structure activity relationships. Basically, it's the same. The thing with machine learning and statistics, every field likes to use their own kind of terms. The biologists would say bioinformatics, biostatistics, the chemists say chemometrics, cheminformatics. It comes down to the same techniques, more or less. So the concept of this study was, so we wanted to understand kind of the environmental status, wanted to do a risk assessment and also some models, but they kind of converge at the end. So we need to find high quality data. We did find some from the EPA on cell lines on zebrafish embryos. We did kind of tune models, try to train them. And then we got 12 plus 14 models in the end. In the meantime, fish were sampled, and I want to thank Professor Bonassi for the introduction regarding sampling, etc. Unfortunately, we did not have experimental design, so it was kind of random fish were caught, and then kind of blood was taken, plasma was taken, and then this went into kind of chemical and biological analysis. And based on the models and what we found out, which compounds were in the fish, we could kind of do risk assessment. So those were the sampling locations, 4 of them, kind of different gradient of pollution. In total, we measured 400 chemical compounds in river sediment and 90 pharmaceuticals in fish plasma. So the fish are quite loaded with pharmaceuticals, pesticides, etc. The thing with the river sediment is, we kind of see it as a sink for the chemicals, and they always get kind of lifted again, and fish can always consume them, etc. So it's quite the risk. Now when we kind of have the data from sampling, etc., we want to do the models. And the good thing is you have pre-existing or kind of pre-trained models, which are also freely available, and you can use those. One of those tools is so-called Vega QSAR. It's freely available. It's from a Milanese group in Italy, and it looks something like this. So this is Vega. So you take your chemical compounds. I feel this microphone is failing me a bit. Yeah. So you take these chemical compounds and you load them into the tool. So this is what it looks like. So your compounds, which you, for example, have found in your in your river. And then you choose the models which you want to use for your study. So I was interested in the so-called bioconcentration factor. The bioconcentration factor is kind of the capability to accumulate into an organism. Then you have persistence, for example. So you're interested in how long can this chemical compound persist in the environment. And then you kind of can get an output like this. So, for a certain organism, here was the fish fathead minnow, you get kind of, which would be the LC50, which would be the bioconcentration, which would be the persistence, etc. But the problem I had with this tool is so-called chemical space, which was used to train these models. So the fathead minnow dataset is based on 600 chemical compounds. Okay, and there are many chemical compounds which we measured and which are not in this original dataset, because the fathead minnow chemical compounds were mostly pesticides. That means that the model for fathead minnow will have difficulties predicting the risk we have with our data. So it's not well represented regarding the chemical compounds we found in the fish and in the sediment. So I wanted to use my own models, and for those I need data. So you were right with the Menti. And there are a couple of nice data sets out there. One is the ToxCast database, and they did around, I think it's 1,100 chemical compounds on different endpoints regarding zebrafish embryos. I'm not a biologist. I guess you guys know better this than I do. But it's kind of, certain chemical compounds can affect certain developmental issues. And here we have some examples. So it's kind of, I feel there is kind of lacking quality with this data set, but again, this is one of the best we have. So you see some chemical compounds, cause several developmental issues. Some cause only one, some maybe only cause mortality, etc. But it's quite rich regarding chemical diversity, because EPA didn't do only pesticides, but also kind of cosmetics, pharmaceuticals, etc. So it has a larger chemical diversity and could be more representative for the data I have from the river. The next database is the TOX21 database. It's also from EPA, but it's more kind of receptor enzyme based. So it has these nuclear receptors and stress responses, and it has 8,000 unique compounds tested. I say unique because they usually say it's kind of 10,000, but then if you remove, you have some salts which have the same active part of the molecule, etc. When you remove those, you're kind of left with around 8,000. But it's very nice because it has a large chemical diversity, and it's actually kind of very famous for building machine learning models. So the chemical compounds we had in those two, so we have now two data sets. One is 1,000 chemical compounds on zebrafish embryos, and the other is 10,000, 8,000 on the nuclear receptors and stress responses. So how do we build a model? We first need to know which structures we have. Okay, so we said 10,000, and then we came down to 8,000 is because, I removed a lot of those. And then you need to understand your chemical structures. It's hard to do that when you have 10,000, but then you can automatize, with Python, for example, and coding skills, you can automatize a lot of the work and remove a lot of the stuff there. So, and your molecules, they need to kind of, be accessible for the computer, kind of to become numbers. So this is what it's done. Each molecule is an object, or many different objects in a coordinate system. Then we have a lot of those data preparation steps. So removal of mixtures, conversion of structures. You see, one structure can be represented with many different kind of drawings. It's the same structure. So there are kind of rules to this. You need to remove duplicates. You need kind of also to have a step of manual inspection, and then you end up with having a curated data set. So there is so this is where most of the work goes. But luckily there are rules to it. There are nice papers which kind of give suggestions how to do that, etc. We're interested mostly in the active part of the molecule. Is the assumption if you have I don't know, sodium salt, which most drugs come as salts. So you have a sodium salt. It's the assumption that it's not the sodium ion, which is kind of toxic, but the active part of the molecule. So we want to kind of assess the active parts of the molecules. And this is what the data looks like. So raw data, you have a zinc double salt, for example. This is what we want to get out of it. Or here you have a kind of a hydrochloride, which is a drug, and then this is what we want to get without HCl. Or this is potassium salt. So here, K+. This is what you want to get in the end. So there is a lot of work around those. So chemicals become matrices. This is what happens in the background. And based on these matrices, you calculate so-called descriptors. So the descriptor is kind of something characteristic about this molecule. I gave you some example. One is kind of the ionization potential. You probably know it from school. One is kind of the home volume energies, it's in the orbital. So those are descriptors specific for the molecules. And altogether, this is called chemical representation. So this is information you have about chemical compounds. You can do fingerprints, you can do descriptors, you can do many different things, but kind of the overall term is chemical representation. So how do you describe a molecule to a computer? One kind of, this is, there is quite a hype about it, are so-called fingerprints. So there is an algorithm which kind of divides the molecule into substructures, and then based on these substructures, you get kind of bit vectors like this, if there is a certain substructure present or not. These were kind of the substructures which were quite important in this work. So you see kind of aromats mostly, where if you have kind of some polar stuff, or chlorine or fluorine, etc., those were kind of very important in kind of when you make the decision that the molecule is toxic from the algorithm. So those groups were quite important. So this is also chemical representation. And now the modeling part. I have it actually all in one slide. So we need our molecular structures. We need our descriptors or chemical representation. So this is the information about the molecules. If it's hydrophobic, if it's big, if it's small, how polar it is, the topology in general, etc. And then you can go for kind of multivariate analysis, but we want kind of more complex thing. We want nonlinear. This is why we go into machine learning. And then we want to understand how these molecular descriptors are related with the activity we wanted. So it comes down to if a certain substructure is present in a molecule, we say it might be toxic or not. This is what it kind of, this is in a nutshell. So if you have, kind of an aromatic ring and you have maybe a chlorine attached to it, it might be a toxic molecule. It gets far more complex than that. But basically, you want to understand these relationships. And once you understand these relationships, you can extrapolate. You can do it for the other molecules where you don't have the data. So the model says, if we have this chemical structure, we know it's toxic. We know the rule. It's also like with how do doctors recognize that the child has asthma, for example? So you see the child after you've seen thousands of those children, and then it coughs, it wheezes, it's allergic from April to June. It has some of the biomarkers quite high, and then you kind of infer, okay, this child has asthma. So you have seen a lot of those, and this is the same with the model now. So the model has seen a lot of compounds. It knows whether they are kind of toxic or not towards a certain endpoint, and it learns the rule. And once we know the rule, we apply it elsewhere. For my study, it was something like this. So we have chemical representations, the information we have about chemical compounds. We have the toxic endpoints from the databases, nuclear receptors, stress responses, fish development, etc. Data preprocessing, splitting into train and test set. So you need training data. Okay. Here you kind of optimize the models. I did a couple of those. And then if the models have a certain quality, I choose them for later extrapolation. So I have to be very strict about these models if I want to extrapolate. I can't, if a model has a low accuracy, I can't use it. So with those who have high accuracies, I save them, and I can use it later for the compounds. So 2 data sets, TOX21 and TOXCAST, trained models, applied those with on the compounds which we found in the Sava River. So this was the whole pipeline. Yeah.
That excluded for the test set. It's a totally different.
Yeah. So this is me validating my model. Yeah. But then, before I go into extrapolation, I don't have this step here, but before I go, so this is me checking the models. And once the models are kind of satisfy these criteria, then I take the whole set and retrain to get kind of. So this is kind of for picking which endpoints have a lot of information. This slide is super relevant. So you have to be very careful with the metrics. Okay, so do you remember kind of the whole COVID thing, and then people used to say, you know, the small tests, they had kind of 96% accuracy, etc. So it's quite relevant to use other metrics as well. So if a compound is toxic, you know, if it's really toxic in the data set, and we predict in the model that it's toxic as well, we call it the true positive. If it's not, and the model predicts it's not, we say it's a true negative. Okay, and then we have these two, which are quite tricky, because if a compound is toxic, and the model says it's not, it's a false negative, and this shouldn't happen. The same goes for, you know, if the compound is not toxic or negative, and the model says it's toxic, it's false positive, but it's less of a risk than this one. Okay, and then based on those, you have different metrics which you can calculate. And you know, using accuracy is not the best choice, because you see here, it sums all your instances in the model or your molecules. And here in the upper term, you have only true positives and true negatives, meaning it's insensitive to false negatives. Okay, this is why you have these others. You have sensitivity, you have specificity, etc. So if you go into kind of cancer, you know, saying for a person which has cancer in the model that it doesn't have cancer is a problem. So, you know, we have to be kind of thinkful about which metrics to use. I usually use the matrix correlation coefficient, or the kind of the balanced accuracy, and they're much more sensitive comparing to accuracy to such imbalanced data sets. So the data sets we used here are imbalanced. So most of the compounds are not toxic. So you have just a few which are toxic. And then if you say, you know, you can say my model is 99% accuracy, but then you had, I don't know, like 20 compounds which were actually toxic and you didn't catch them. It won't be reflected in accuracy. Okay, so other metrics have to be used. I think I have it in my slide. Yeah, it's this one. Okay, so the results. So this was kind of a spin-off of my work, but I think it's worth mentioning. So you see, this is the accuracy, and this is the matrix correlation coefficient. So there were models trained which have almost 100% accuracy. Here, the line, and had a 0 matrix correlation coefficient, meaning they were random towards the toxic compounds. Okay, so we had just a few toxic compounds, and they were misclassified. And then, you know, if you have 10,000 and, you know, 100 get misclassified, then it's still kind of 90 plus something accuracy, because you miss just a few of those false negatives. But then the matrix correlation coefficient, you can't escape it, you know, it will kind of understand what went wrong. So it's very important to be kind of mindful about those. Here is an example of, just a look. This is the Cohen-Kappa score. Okay, maybe this one, balanced accuracy as well, you know. I feel still matrix correlation coefficient is probably, so you have random models which have a high balanced accuracy. And it's just because of this imbalance in the data. So when trying to do a model, be mindful about this. And then, you know, when I see papers, you know, people publish, you know, we have 90% accuracy in a model. You know, if you don't show these others, I don't trust you. Yeah, and then It turned out from these data sets, so these were the criteria I set, the matrix correlation coefficient, cross-validation, so you can cross-validate your model, so you split, train, test, split, train, test, etc. And then I had this external validation set. And you see for most of these zebrafish endpoints, they're kind of below this 0.2 or 20% matrix correlation coefficient. And that means they're random. We can't predict toxicity from chemical structures. Okay, so accuracy would be high. You saw this? Accuracy would be, I don't know, sometimes even 100%. But then most of the models are random. Okay, there is no correlation between the kind of true toxicity and what we found here. Only a couple of models satisfied these criteria, so most of them have to be discarded. Okay, so there is no rule we could find between chemical structures and toxicity towards the zebrafish endpoint. Okay, so we don't know why these developmental changes or effects happen. Okay, so it's either, I don't know, maybe sometimes the mixture, or I don't know, or in general the data was bad, maybe. You know, so I just picked those were kind of which kind of have passed my super strict criteria. Yeah. I think it's 96 hours. Yeah. But this is kind of, I think this is the largest zebrafish study so far. And they have many papers published, but I feel it's rather low quality regarding kind of building models on chemical compounds. Okay, so I had my models. Some of those kind of passed this strict criteria, and then I used them for extrapolation. So let's go maybe back here just to remind you. No. Yeah, so I had this criteria, super strict criteria with the matrix correlation coefficient, and only a couple of models kind of passed this criteria, so I would use them for extrapolation. Why? Because I want to find out, based on chemical structures, which compounds which we measured in the Sava River, so in both fish plasma and in sediment, might have kind of toxic potential. Okay, this is why I extrapolate. So I built the models, I didn't let them all pass. Now I have them, I saved them, and now I do extrapolation. Oh, there it is. Okay, now I kind of had 7 + 12, 19 models out of, so I kicked out, I think, 7 models. And I calculated each time, each molecule which we measured was predicted as being toxic or not. So if it's 0 or 1. And what turned out was that most of the chemical compounds were actually not that toxic. So they would have kind of 1 out of the 19 endpoints where they had a prediction, or maybe up to 6, but most were 0. The reason is most of the chemical compounds we found in the environment, so in the fish and sediments, were pharmaceuticals. And actually, they shouldn't be that toxic. So, you know, if it's kind of not toxic to humans and the humans can take them, then it shouldn't be that toxic. So we don't have so many pesticides. Those which had 5 and 6 were mostly kind of pesticides, which is a sanity check for us. You know, that you know, even though there are pharmaceuticals in those fish, it doesn't have to have the detrimental effect. But then again, I'll go back to where I started. This is the best we have. So we don't have, you know, we can't do with each of the chemical compounds, we can't do studies. So we use models to kind of estimate the risk. Yeah, so coming to my conclusions. So when lacking tox data, we can try to build models. Machine learning, I didn't talk much about machine learning models, but I have to be honest with you now, with ChatGPT, it's quite easy to do. So you have R, you have you know, Jupyter notebooks. You know, if you can kind of read in, you can look for data, It can generate code for you, etc. So it's actually much easier than it was a few years ago, and just go for it. But it needs data. It needs a lot of data. We can do both linear and non-linear kind of multivariate models, and we can use those for risk assessment. So, but be mindful. This is a lot of extrapolation. We're going we have error propagation here. So you do a toxicological study, you have an uncertainty there. You go into assessing chemical structures, you have an uncertainty there. You go into building a model, there is another uncertainty, then you extrapolate. So there is error propagation in there, but we're doing it because it's the best we can. And yeah, the compounds we found were mostly considered not being toxic or very toxic because they're pharmaceuticals.